Welcome to another video from Morphlab. Today we are going to talk about maps. Did you know that if you drop a map on the floor, there will always be a point that touches the exact point it refers to? Let's say this is a city, and now let's say we drop the map of this city somewhere just randomly, like this. The map is highlighted in yellow. Now, each location inside the city has an equivalent point on the map. For example, this point on the corner is here on the map. Or this point at the tip of this narrow region is here on the map. But there is one point in the city that matches its equivalent point on the map exactly. And you can probably say it's somewhere around here. Here we are going to prove why there is always a point matching its exact location. And by the way, for this proof we are not going to use any mathematics. And then we are going to see how to find this point. You can pause the video here if you like to think about it, and when you are ready, continue watching. Assume that we drop the map of this city randomly somewhere. Now, every location in this city is mapped inside this yellow region. Just think about it again. If all the locations in the city are mapped to this small yellow region, what about the locations under the map itself? Of course, those points are mapped into a smaller region inside this yellow small region. Let's say something like this. So this red region is the equivalent of those points of the city which are under the yellow region. Now you just need to repeat this process again, finding the equivalent locations of the points of the city which happen to be in the red zone. Those are mapped inside a smaller region inside the red zone. As you can see, this just points to a smaller and smaller region inside the map until it's just a single point, and that is the point we are looking for. A point on the ground which is mapped onto itself on the map. Let's see what is happening here. A map is the result of three possible transformations. The first one is obviously scaling, meaning everything is now smaller than its real size. The second thing that is happening here is rotation, because as you can see, the bottom edge is not parallel to the bottom edge of the map. It's a bit rotated. And the third thing is translation, meaning the map has just moved because it could be placed anywhere in the city. Scaling changes the size but does not change the angles. As you can see, the shape of the map is the same as the shape of the city. Rotation also doesn't change the shape, it just rotates the whole thing. Translation is a simple move from one point to another, keeping the same angle. Now let's see the whole concept for a simple case. Let's say you have a city here shown as a big rectangle and the map of the same city in yellow. Let's assume that G is a segment of a street or just a length in the city, and the equivalent of that on the map is M. So simply what we have is this. Now, as we said before, three things have happened here, but let's just focus on the rotation and scaling. Ignore the translation for now. We first rotate M as much as phi about the point O. Let's just forget where the point O is. Let's assume we know its location. We then scale up the segment M, and then M turns into G. And if you want to go from G into M, you can do the whole thing in reverse. Here you first scale down and then you rotate. Now, any other segment can be transformed back and forth between the map and its actual location using the same point O. As you can see, location of point O itself does not change by rotation or scaling about itself. And as you have probably guessed, the point O is the point we are looking for. It's the point which stays the same under rotation or scaling. But how do we find this point? The only thing we have are M and G, and of course the angle between them, which is phi. Now let's try something. Let's bring G next to M and have a closer look. Of course, the angle between them is still phi. Now let's connect the other ends to form a small triangle. Okay. Also, let's connect the ends like this. Now let's focus on these two triangles. The one in gray and the one in red. These two are actually similar triangles because both of them have the same angle phi, and in both of them, the ratio of the two sides of the angle is the same, is the scale ratio. The gray triangle you can construct easily. The red triangle you cannot because you don't know the location of point O. But there is a way to construct the red triangle from the gray triangle and eventually find the location of point O. We first rotate the gray triangle until the two sides of the triangles overlap. And bingo! Orientation of M now points to the location of O. From here you have two ways to find O. One is to just repeat this process again with another segment and its image on the map. We have then another line which points to the location of O. So intersection of these two lines is the location of point O. Another way is to just scale up the gray triangle about its tip. By how much? By the ratio of F to E, like this. And you just found point O. To make it clear, let's test this method for a map and see if it works. And by the way, if this seems too complicated, stay tuned until the end of the video to see a much easier way to find point O. Okay, let's say this is a city and a map of the city in yellow. The first thing we need to do is to identify a line segment and the equivalent of that on the map. It's easy here because we can just select one of the edges of the city, for example, edge A. Now, first we bring them next to each other, putting the big one next to the small one. And remember, here orientation matters. Don't put the wrong ends together. So here we have the image of the original segment next to the small version of it. Now we connect the ends like this to create a triangle. We also connect the ends like this. And now we have a triangle that we need to rotate. But how much do we need to rotate this triangle? Until we bring the two dashed red lines together, which after rotation becomes like this. And the new edge points to the location of point O along this line. Somewhere on this line locates point O. We can now scale up the triangle until the tip of it touches the end of the big segment. And now the other end of the triangle shows point O. Just to show you that this works with any other edge or line segment, let's repeat the whole process, this time for segment B. Again, first we bring the segment next to the small version of it. We then connect the two ends to form a triangle. Also, we connect the two ends like this. Now we find the angle for the rotation of the shaded triangle, and that is the angle to bring these two dotted blue lines together. We rotate, and now we have another line pointing to the direction of point O. And of course, if you scale the triangle until the tip of the triangle touches the end of segment B, the big version of segment B, on the top right corner, the other tip shows point O. And as you can see, it works no matter which line segment you choose. Now let's clean up the whole picture. Okay, if O is the fixed point, we should be able to use rotation and scaling, both of them about the same point O, and get to the city from the map. First the rotation, then scaling about the same point by going along these lines, which of course if you scale it up, you get this. Voila, it works. Problem solved. Now that you learned the complete detail of what is happening here, as I promised, here is a much easier way to solve the problem and find point O. Let's first get back to the original figure we used. We extend the two segments until they intersect. This new angle which is formed is also phi because it's clearly the angle of rotation from M to G. We now draw a circle through these 3 points, the intersection point and the two equivalent points. But since the angle at O is also equal to phi, point O falls on this circle, and that is the magic solution. Because if we just do it again with another point and its equivalent, we get a new circle which intersects this circle at point O. Point O can be found by just drawing two circles and finding their intersection point. Let's do this for the example we just had. Let's find intersection of the two equivalent lines, for example here the top edge, and we select 3 points, the intersection point and the two equivalent endpoints. We draw a circle through these 3 points, and now we do it again for two other endpoints. And the intersection of these two circles is the point O we are looking for. There you go. Hope you enjoyed this video and thanks for watching.